In this example, let's consider a salmon jumping out of the water with an initial velocity of 6.2 meters per second. And let's try to answer the question, how far can the salmon travel, so delta x, before hitting the water again with a splash? To answer this question, I have to think about the fact that I can divide up the world into x and y coordinates. And that's exactly what we have to do. We have to divide this velocity, and then whatever happens to it, into x and y parts to think about. So let's do that. Let's talk about the initial velocity in x and the initial velocity in y. For that, we need to know the angle here. So let's say the angle is 10 degrees. In that case, Vix is the initial velocity times cosine of that angle, which is 6.2 meters per second times cosine 10 degrees. And if I do that out, it's 6.11 meters per second. If I do y, Vi sine theta equals 6.2 meters per second cosine, sine 10 degrees, and that is 1.08 meters per second. And the way I chose sine and cosine was just looking over here and saying x is the adjacent side to this angle, so I use cosine, y is the opposite side to this angle, so I use sine. Now answering the question of how long or how far can this thing travel seems tricky at first, but here's a handy fact. Because this situation is basically symmetric, so imagine the salmon starts going up, and at the end he's going down. And the thing that changed the velocity had to be an acceleration. So if I have a change in velocity that's not zero, then I had some acceleration that's also not zero. And the only force that could be causing such a change in velocity here would be a force from gravity. So we know that the y part of the velocity changes because of gravity, but the x part stays the same the whole time. So if I checked the x velocity at any time, it will always be this. That is, there is no x acceleration. And in general, for problems in kinematics, that's going to be true. You usually won't have an x acceleration. You'll just be dealing with a y acceleration, and that's gravity. Well, consider this. Gravity is acting the same way at every point along the path. So no matter where I check, we always have an acceleration that's gravity pointing down. Everywhere. And what you can get out of that is that whatever my initial y velocity is here, it's going to be exactly the opposite of my final y velocity. So v final in y is the negative of v initial in y. And using that, I can figure out how long the fish was in the air, and then it's a pretty simple matter of deciding what, or calculating out the change in x position. So my initial y velocity was 1.08 meters per second, and we know that that is the opposite of my final y velocity. So let's write this out. Final velocity in y will be equal to initial velocity in y plus the acceleration due to gravity times time. And I just told you that Vfy is equal to negative Viy. So if we substitute in numbers, we get negative 1.08 meters per second, the negative of Viy, equals 1.08 meters per second, just Viy, plus negative 9.8 meters per second squared times the time in the air. Now, normally you would just want to do this symbolically first and plug in the numbers only once you had t equals something, but I wanted to really hammer home the trick that the final velocity in y is opposite the initial velocity in y if acceleration is our only if the acceleration due to gravity is our only vertical force or vertical acceleration. Being sloppy with my terms there. So if our only acceleration in y is due to gravity, then, and it's a constant gravitational field, so applying the same everywhere, like on the surface of the Earth, then we can use the trick that my final y velocity is the opposite of my initial y velocity, and it just simplifies things a whole bunch. And if you do out the algebra here, you find that the time the fish is in the air is 0.22 seconds. And we already decided that there's no x acceleration, so now finding delta x, the equation is simply the initial x times time in the air. So delta x equals 6.11 meters per second times 0.22 seconds. And when I do that, I get 1.34 meters.